Hello. My name is Andrew Wilkey. I'm going to talk with you about some of our work in anti-PT symmetric dynamics using delay-coupled semiconductor lasers at IUPUI. So basically, this is PT symmetry with built-in time-delayed coupling, when you can't ignore the time delay inherent in coupled oscillators. So our system, we have a cartoon of our system here at the bottom. I have two semiconductor lasers, 1 and 2. I operate them at slightly different optical frequencies, and I send light from one laser into the active region of the other laser and vice versa. Now, because these lasers are separated physically in space, we can't ignore the time delay between them due to the fact that light has to travel between the two lasers. So this time delay is greater than the intrinsic timescales involved in the laser dynamics themselves. So we can't ignore it. And of course, I can control how much light I let go between the lasers by placing a glass slide in between them. So I'll get into this later, but we're going to investigate the effects of this time delay on PT symmetric signatures in our system. So a brief outline, I'm going to give you a brief introduction to PT symmetry in optics. I'll then introduce our system with a model and some defining equations. Then I'll give an example of some intensity behavior in these lasers and how they're affected by time delay, starting with an eigenvalue analysis, some predictions, and then I'll present some basic results, both numerical simulations and experimental results. So I don't have to explain this too much, thankfully, but I'll give a brief introduction to PT symmetry here. We know in standard quantum mechanics, we generally require Hamiltonians to be Hermitian because it ensures real eigenvalues, unitary evolution, and probability conservation, right? But you can get real eigenvalues another way. You can have a Hamiltonian commute with the PT operator. In other words, it's PT symmetric. So under certain circumstances, a PT symmetric operator can exhibit real eigenvalues. Of course, the parity operator reverses your system in space, and the time operator reverses your system in time. And this allows for an extension of quantum mechanics to open systems and complex space, right? This is all things we know. You can also have a class of non-Hermitian Hamiltonians that can be called anti-PT symmetric. And all this means is that the Hamiltonian anti-commutes with your PT operator, as seen in this bottom right-hand corner here. So typically, when you have PT symmetry in classical systems, you talk about anti-PT symmetric dynamics because your rate equation model will not have the I from the Schrodinger equation. So for the sake of this talk, it's a minor detail, but we are going to work in the basis of anti-PT symmetry. Okay, so the prototypical example of PT symmetry in optics is the coupled waveguide. Right, so I have in this upper right-hand corner, I've given you a diagram of this coupled waveguide. So what I do is I have these two waveguides next to each other. I send light down longitudinally down the waveguides, and due to the evanescent coupling between them, light can leak from one to the other. And we characterize that coupling by kappa here. And I pump one waveguide optically at a rate gamma, and the other waveguide is naturally lossy. So it loses light at a rate of minus gamma. If you write down the differential equations governing the evolution of the electric field in these waveguides, you find that you can describe these waveguides with an effective Hamiltonian given by this expression here, which is not Hermitian, but it is PT symmetric, which is easy to check in this situation here. The diagonal elements are your gain and loss terms, and the off diagonals are your coupling strengths. Now we can solve for the eigenvalues of this system, which will in turn tell us about the evolution of the electric field of the system. And we see that depending on the relative strength of the gain and loss term to the coupling term, we get dramatically different behavior because of the eigenvalue transition from real to complex. So if I have gamma less than kappa, I have real eigenvalues here. And vice versa, if I have gamma greater than kappa, then I get imaginary eigenvalues. And because the eigenvalues show up for the electric fields as e to the I lambda t, I expect either bounded electric fields or exponentially diverging electric fields. And at the location where this transition occurs, in other words, where the coupling rate equals the pump rate or the loss rate, that is called the PT transition. So what I'm going to do is I'm going to show the intensity in the waveguides as a function of the ratio of the gain and loss parameter to the coupling strength. And this is what we see. When that ratio is less than about 1 or less than 1, the intensity in the system is bounded. So it never gets too big, never gets too small, right? When that ratio is greater than 1, we see divergent behavior. So there's dramatically different behavior depending on the value of that ratio of the diagonal to off-diagonal terms are PT symmetric Hamiltonian. So there are some drawbacks to the coupled waveguide experiment. First is that it's hard to exactly balance gain and loss because they come from two different mechanisms. It's also hard to continuously vary the coupling rate between them. These waveguides are embedded on chips, so you need precise fabrication. If you want to change the coupling rate, you need to make a new chip with these waveguides on them. Our motivation is as follows. We wanted to develop a PT symmetric optical system that is robust and can be made with off-the-shelf components. So it's easy to set up. We have the equipment in the lab already. That was our motivation for the system I'm going to present today. We also wanted to examine the effects of time-delayed coupling. So in the waveguide model, the coupling is instantaneous. It's transverse. What if you can't ignore that time delay for light to go between both oscillators? So that's what I'll discuss with our system here, these two coupled semiconductor lasers. It turns out that the gain and loss is exactly balanced in our system because it's replaced by the frequency detuning between the lasers. We can easily control the coupling continuously by placing coded slides in between the laser's optical path. And we use equipment that we already had in our lab. So there's nothing fancy, no precise fabrication needed. And of course, we have this built-in time delay due to the physical separation of our lasers. So to model our system, we're going to use the Long-Kobayashi rate equations for semiconductor lasers. So these are, this is a model that has been well studied. It's shown to reproduce semiconductor laser behavior very, very well. It's been around for a long time. It is a set of, for two lasers, it's a set of 4 coupled nonlinear differential equations. So the first 2 equations at the top here describe the evolution of the electric fields in lasers 1 and 2. And the bottom equations describe the evolution of the carrier inversions in the lasers. So just explaining what some of these letters mean, E is going to describe the electric fields in lasers 1 and 2. N are the carrier inversions in lasers 1 and 2. This delta omega term here is the frequency detuning between laser 1 and laser 2. So their frequencies are mismatched, and the measure of that mismatch is this delta omega parameter. The last term has the coupling rate kappa, and then there's this term here that has the explicit time delay. So we see that the rate of change of electric field 1 depends on the value of electric field 2 evaluated at a time earlier. And that earlier time is tau, which is the delay time for the lasers. So we have our built-in time delay through that last coupling term in the first 2 equations. Now our goal is to get something that resembles PT symmetry for 2 coupled oscillators. So we want a Hamiltonian model, 2x2 Hamiltonian model for these lasers. So we're going to try to massage these 4 rate equations into 2 rate equations with an effective Hamiltonian given by that shown in this box on the right. So this is our goal Hamiltonian, a PT symmetric Hamiltonian with these eigenvalues. Let's see if we can make some suitable approximations and get an effective Hamiltonian model for our coupled lasers. So the first approximation we're going to make is that our lasers are operating in the steady state, which means that I can write my solutions for the electric field as e to the lambda t, which means I can rewrite my delay terms like here on this last line. And I'm also going to operate these lasers just above threshold. So I've turned them on just to the point where they've started to laze, which means that I can ignore the carrier dynamics because the carrier inversion above 0 is pretty much 0. This lets us reduce the 4 coupled rate equations into 2 coupled rate equations with an effective Hamiltonian given by this matrix here. Now you can see that I still need to make another approximation to get it to be PT symmetric, because it still includes this lambda tau term up here. So for the sake of simplicity, let's just assume that there is no time delay. I'm going to make things really simple. Under that approximation, this effective Hamiltonian reduces to that on the bottom left, where so in the absence of time delay, the effective Hamiltonian is exactly what we wanted with our goal Hamiltonian, where the diagonal elements are the frequency detuning between the lasers, the off diagonals are the coupling rates between the lasers, and we see that the eigenvalues can be real or complex depending on the strength of those parameters. So in contrast to the coupled waveguides, we see now that the diagonal elements, instead of being gain and loss, are the frequency detuning, which has the added benefit of always being equal and opposite between the two lasers. So that solves one of the experimental challenges. So again, I expect dramatically different behavior depending on the relative ratio or the relative strengths of the frequency detuning and the coupling rate, because the eigenvalues go between real and complex. So let's take a look at the intensity output of these lasers. What do these lasers intensities look like as a function of that detuning parameter, that gain and loss parameter? So we'll plot the intensities of those lasers. We know the intensity is related to the electric field by E mod squared. What I'm going to do is I'm going to numerically solve those four coupled rate equations with all the complexities and the nonlinearities in there. And that's what I plotted down here in the bottom left. So in the absence of any time delay, we expect a completely PT symmetric model. And that's what we get. So I plotted the intensity versus the ratio of the frequency detuning to the coupling strength. In other words, the gain loss parameter to the coupling parameter. And I see that there's a dramatic phase transition right where that ratio is equal to 1. So I get a PT transition where I expect it, where below that transition point, I get exponentially divergent behavior. And beyond that point, I get bounded behavior in the intensities. Right, so that's exactly what we expect based on our effective 2x2 Hamiltonian model for zero delay. So now what I'm going to do is I'm going to increase the complexity and I'm going to introduce non-zero time delay. So again, we don't expect our effective Hamiltonian to be PT symmetric anymore, but what we find is that when I actually produce these intensity plots for non-zero delay, the basic features of PT symmetry are there. We see this phase transition where it should be. So what I plotted in the bottom right here, on the left, I have numerical solutions based on the four coupled rate equations. And on the right, I have experimental data. These are both for some non-zero delay. And we see that strikingly, the intensity profiles resemble that for the non-zero case, even with all the added complexities. So there's this bounded intensity behavior when the ratio of delta omega to kappa is less than about 1. And then we get this divergent intensity behavior when that ratio is less than about 1. And then again, on the other side, when the ratio is greater than 1, I go back to bounded intensities. Now the time delay produces two major signatures that are not present for zero delay. One is that there are now these broad intensity oscillations, these very slow intensity oscillations in the region where this ratio is greater than 1 on the bottom here. Now, these are not time oscillations due to complex eigenvalues, but these are oscillations due to the time delay itself. So the real parts of the eigenvalues are transitioning from above to below 0. Furthermore, we see that the PT transition has been widened a bit. So the transition is no longer necessarily when the detuning parameter is equal to the coupling parameter. It's somehow beyond that. So we'll see later that the delay has the effect of pushing that PT transition further to the right and further to the left. So we can widen that transition region. So to understand the intensity behavior, we need to look at the eigenvalues of our system. So I'm going to use our effective Hamiltonian model with the time delay included. I'm going to solve for the eigenvalues. And because the eigenvalues eventually determine the intensity behavior, by understanding the eigenvalues, we can understand the intensity behavior. So we can make predictions and then check them numerically and experimentally. Now, because of the time delay, we find that our effective Hamiltonian is actually infinite dimensional, which will make our characteristic equation transcendental, and that leads to infinitely many eigenvalues. Also, eigenvalues are generally always complex. So things can get a bit messy, but luckily, because we have semiconductor lasers here, we only need to worry about the eigenvalues with the greatest real parts, because those modes are going to dominate the laser behavior. You have all these competing modes in the lasers, but only the ones with the greatest real part will eventually take over and make the laser saturate at some intensity level. So we only need to examine a small subset of the eigenvalues to see what happens to the intensities. And to show that, let's take a look at these two plots on the right-hand side of the picture here. So for some non-zero delay in the upper right-hand corner, I've solved for the eigenvalues of my system numerically, and I'm showing you the eigenvalues with the greatest real parts, only the real parts. And you can see that the behavior of it looks something like this, where you have these oscillations when the detuning parameter is greater than the coupling parameter. And then in the middle, there's a central dome region here. Now on the bottom, I've also solved the 4 coupled rate equations for the intensity profile of that same detuning parameter here. And you can see there's a very strong correspondence between the eigenvalue picture and the intensity picture. So in other words, the intensity profile mirrors what happens with the eigenvalue picture if I only choose to display the eigenvalues with the greatest real part here. So by analyzing the eigenvalues with the greatest real parts, a small subset of the infinitely many ones, we can ultimately make predictions about the intensity behavior of our 2 lasers. So I won't go into detail here, I don't have time for it, but we can analytically solve for 2 things of our system. If I look in the top right plot here, I can solve for the width of these oscillations when the detuning parameter is greater than the coupling parameter. We call that the sideband oscillation width. That's the frequency of the slow intensity oscillations. I can also solve analytically for the PT transition region, the width of that central exponentially divergent dome. So let's take a look at some results here. I'll first start with the sideband oscillation width results. So for the sake of time, I'll just present them here. We have 2 main predictions. One is that the sideband width should be independent of the coupling strength, and that the width is inversely proportional to the delay time here. So these are our results in this figure 1 here. The black line that I plotted here is the analytic prediction, and the points on that line, the black squares, are measurements taken from solving the 4 coupled rate equations. So we see there's excellent agreement between the eigenvalue model and the rate equation model there. The colored data points are experimental data. So again, we see a nice linear trend. The slopes are slightly different, but due to reasons that are, let's put it this way, the slopes are slightly different, but they're within tolerance if you account for some experimental complications here. So again, the 2 major predictions are satisfied by both the numerical results and experimental results, that there's a straight line here, and that the results are independent of the coupling strength. The second prediction that we make concerns that central dome region, the PT transition location. Analytically, we can show that the PT transition should increase non-monotonically as a function of the delay time, and it should do so with these discrete jumps. So I'm plotting our prediction in the upper left-hand corner here. Just take a look at the solid black line. For 0 delay, we expect it to be 1. That's the typical PT transition. And then it has a sharp uptick, it keeps going up non-monotonically. So numerical simulations seem to match that prediction very well. Again, that's what I plotted in the top right corner here. Our experimental results look a little messy, but the main features are still there. So this bottom right picture is our experimental results for the dome width, the central PT transition region. So we see that there's a general overall increase of the PT transition. So the numbers go up, and there are these spiky jumps that occur at the locations where they should based on the prediction here. So again, the two main features of the prediction are met, even though the exact form may not agree 100%. So I'm going to conclude my talk there. I think I'm out of time. So I'll say that we have a very versatile system capable of probing PT symmetric dynamics in optics using off-the-shelf equipment. We see signatures of PT symmetry even in the presence of time-delayed coupling and added complexities due to nonlinearities. We can analyze the system using an eigenvalue analysis, and there's good agreement between theory, numerical simulations, and experiment, even with increasing complexities going from one model to the other. So I'll end my talk there. I thank you for listening, and I'll take any questions you may have.
Okay, thank you, Andrew. And is there any question, quick question?
Yes, I raised my hand. I don't know if you...
yeah, please go ahead, unmute yourself and go ahead.
Yeah. Yeah, hi, thanks for the nice talk. I had a couple of questions. So in the end, I didn't understand whether it was important or not that it was the Hamiltonian was anti-PT symmetric or PT symmetric. So I was a bit confused about this part. So can you say something maybe more about this?
Yes. So for the sake of this talk, my only point about mentioning anti-PT symmetry was if I take a look at my eigenvalues here on this slide, we choose to work in a basis where real eigenvalues correspond to exponentially diverging electric field amplitudes.
Oh, okay, okay.
Yeah, that's the really only main point for this talk.
Yeah, okay. And then also in this slide, so why do these numerical simulations and experiments seem not to match, or is there something that I'm missing? So the scales of the two plots are kind of different. So are they supposed to match, or I'm missing something?
They're supposed to match within experimental, I don't know, uncertainties. So that the scale on the intensity axis, the y-axis, these are arbitrary units, so I don't expect them to necessarily match perfectly, just due to the way we measure the intensities in the lab versus with numerical simulation. The frequency of these broad intensity oscillations do not match, you're right. But that is just because they are taken for two different delay times. So on the left plot, the delay time is different than what it is in the right plot.
Okay.
Yeah. My point for having them side by side was just to show that the overall features were the same.
Okay, so it seems there is no other question. So thank you, Andrews, again for your talk.